Hello everybody. Today I would like to talk about adding sine waves and look at interference, both constructive interference as well as destructive interference as a function of phase offset between two sine waves. And in order to do so, I would like to use the phase calculator. And in the heart of our phase calculator, we will find the familiar oscilloscope. Oscilloscope is time domain showing you amplitude over time, where amplitude is shown on the y-axis, linear scale, no decibels whatsoever, linear scale with a zero value in the middle, goes all the way to +2 at the top and drops to -2 at the bottom. Time, however, is not expressed in milliseconds or seconds, but is expressed in degrees phase. And for a single sine wave to complete one revolution, it has to complete a 360-degree revolution to get back where it started. So 360 degrees of phase to express time rather than seconds and milliseconds. And in our oscilloscope, we have two waveforms, two sine waves, if you will. There are sine wave A and sine wave B, where B is blue. And the only reason that we cannot see sine wave A is because it's currently living underneath sine wave B. Sine wave B is masking sine wave A, so to speak. But if I temporarily introduce a phase offset 30 degrees, then cuckoo, okay, now we see B shift, the blue sine wave shifted, revealing sine wave A, the green one, which was living underneath it. Okay, so let's take that offset out. They end up living on top of each other again. And in the oscilloscope, we can add A and B together. And that is a simple matter of addition and subtraction, primarily addition in this case. Because let's look over here at our waveforms. Both A and B have the same amplitude. They have a value of 1 at that particular point in the waveform. And surely if we add 1 and 1 together, we get something which is twice as tall. And therefore the peak-to-peak ratio, the ratio of this peak with respect to the ratio of those peaks, is currently 2:1. And as you're well aware, a 2:1 ratio, which is shown over here, of the red sine wave, which is the sum of A and B together, a ratio of 2:1 is an increase of 6 decibels. So two sine waves that live perfectly on top of each other and are equally loud will gain 6 decibels when added together with a 0-degree offset at equal loudness. These are the requirements for that 6 dB increase in level. However, there's also another way of looking at this kind of interaction, and for that I would like to go to the phasor scope, which is another way of visualizing the same phenomena. The phasor scope shows us phasors, where phasors is a portmanteau, which is the addition of two words together. It's a portmanteau of the word phase and the word vector. And if you take the first syllable of the word phase and the last syllable of the word vector, you are going to get phase vector, you're going to get phasor. And if we think of those signals, those sine waves, as phasors with a certain magnitude and a certain direction, then it greatly simplifies the understanding of adding those signals together. So right now we have our B signal, which is masking our A signal. They have the same direction, the same orientation, and both signals have the same length, the same magnitude. So surely if we add two of those segments together, we're going to get something which is twice as long, twice as tall. Again, a 2:1 ratio, a 6 dB increase. However, we can introduce a phase offset, and that phase offset, let's do 30 degree once more, on the oscilloscope will cause a shift, because our major divisions are 90-degree divisions, whereas our minor divisions are 30-degree divisions. So these are 30-degree divisions. And if we look at our sine waves, then we see that B has been shifted to the right by one minor division. So everywhere we look, it's moved over in time by 30 degrees, which is, of course, different amounts of time for different frequencies, but the same principle applies. It's moved over in time by 30 degrees. Everywhere we see the same 30-degree shift. That angle can also be observed on a phasor scope, in which case it is literally a 30-degree angle between my A phasor and my B phasor. That is the 30-degree angle, the same 30-degree angle between my phasors. On the phaserscope, we call it a phase angle. On the oscilloscope, I tend to call it a phase shift because it's the shifting of the phases. And if you apply your parallelogram, which some of you might have learned during physics, then you can add those two together and calculate the length of the sum, the resultant, and surely that one is no longer going to be equally long as it was when both phasors were pointing in the same direction. And this is the interaction that I would like to study. So if we start to introduce a phase offset, my B phasor is going to go counterclockwise, and sooner or later it will come back where it began. It will have finished a single revolution after 360 degrees, which only leaves 358 intermediate values to look at. So let's reset our phase offset, and let's start from here. We are equally loud, we have matched levels, and that means that if we add our sine waves together, we get twice the amount of amplitude, and 2 times more amplitude is a 6 dB increase. My peak-to-peak ratio is 2:1 at this point. That's twice the amount of amplitude, and twice the amount of amplitude is a 6 dB increase. So what changes if we now start to incrementally add phase offset? Maybe 10 degrees, maybe 20 degrees. Let's go to 30 degrees. Let's go to 40 degrees. Let's go to 50 degrees. Now let's stop at our first milestone, 55 degrees. With 55 degrees, we're saying that the angle between my two phasors is currently 55 degrees. That is the 55 degree angle. On the phaserscope, it is very easy to see. There's the 55 degree angle. And 55 is, of course, close to 60. It's 5 degrees shy of 60, and 60 would be 2 minor divisions. That would be 60 degrees. So everywhere we see the 55 degree shift, we're seeing a shift of almost 2 minor divisions, which would be 60 degrees. We're not there yet, but almost. This is 55 degree shift on the oscilloscope, and the phase angle on the phaserscope. Now, why do I stop at 55? What is so special about 55 degrees? Well, notice the summation. Okay, at 55 degrees, we're in the process of adding 0.9, roughly 0.9 over here for both A and B. Those are their values at that point in the waveform. We're adding 0.9 and 0.9 together, which no longer gives us 2, but gives us 1.8. That is 1.8 times more than either A or B alone. So the ratio of the peak in the sum signal, which is our red waveform, with respect to the peaks of either A or B together, that is now a ratio or factor, if you will, of 1.8, telling us that the peak of the red sine wave is 1.8 times taller than the peak of either A or B alone. And what is so special about that value? Well, 1.8 in decibels turns out to be exactly 5 decibels, no more, no less. And now you see the appeal of 55 degrees, because at 55 degrees, you are going to get exactly 5 decibels, no more, no less. An easy to remember 5, 5, 5. At 55 degrees, 5 decibels of summation. It's 1 dB less than you would have had with 0 degrees of offset, but it's still 5 decibels of summation. So you've lost 1 dB, where 1 dB on average is the just noticeable difference for level. So this is barely noticeable to vast majority of all people out there in the world. 55 degrees, still 5 decibels of summation. 5, 5, 5. Okay, what if we increase our offset and go to 60, and then go to 70, and go to 80, and then we reach our next milestone, which is 90 degrees. At 90 degrees, for those that understand the Pythagorean theorem, it should be readily apparent what the level will be of both signals summed together. After all, for those that remember that A square plus B square equals C square, we should be able to apply that, and figure out what the length is of the so-called resultant, because A and B are now at a straight angle with respect to each other. And this is a length of 1, this is a length of 1, and 1 to the power of 2 equals 1, and the same goes for the other guy. So this is the length of that phasor, the resultant will be the square root of 2. And the square root of 2 happens to be 1.4. If we put that into a calculator, if we take the square root of 2 by pressing 2 square root, we indeed get 1.4. So there you see the proof of concept. Okay, there is the 1.4, and that value that we have over here is also shown over here in the information regarding the sum of A and B. And 1.4 to 1 telling us that this peak is 1.4 times taller. It's about ratios, telling us that this peak is 1.4 times taller than either A or B alone. That's a factor again, a factor of 1.4, tells us that with 90 degrees of offset, you only get 3 decibels of summation, no longer 6, because in order to have 6, you need to have a 0 degree offset. And at this point, you have a 90 degree offset. And there's a very easy way to remember that milestone, which is to think of a clock. We all know that if this is a clock, then these arrows could represent the hands of the clock. And if this is 12 o'clock at the top of the clock, then this puts us at 3 o'clock. And between the hands of the clock, there is a 3 dB offset. There's a 90 degree angle, a 90 degree angle between the hands of the clock. And that means that at 90 degrees, you are going to get, at 3 o'clock, you're going to get 3 decibels. 3 o'clock, 3 decibels. That's how you can memorize. Very convenient. 3 o'clock, 3 decibels. 90 degree phase angle, 90 degree offset. Okay, so let's go beyond 90 degrees. Let's go to 100 degrees and then continue to 110 degrees and stop at the next milestone, the third milestone, which is going to be 120 degrees. Because at 120 degrees, something interesting happens. Notice that if I draw an imaginary line over the peaks of all signals, that the peak-to-peak ratios of all those signals remains 1/1. Everywhere we look, we see a 1-to-1 ratio. And that means that if we sum these two signals together, we don't gain anything and we don't lose anything. The level stays the same. It's also very easy to see in our phasor scope. It's easy to see that with a 120 degree angle, this is the 120 degree angle that we're talking about, that the resultant has the same length, the same magnitude as either A or B alone. And the way that I remember this, the rule of thumb that I remember this, is that I always have to think of three-phase utility power, where the phase angle between the three phases is 120 degrees, because that is how the coils in the generator have been arranged. That's how I remember that 120 degrees doesn't gain you anything, but it also doesn't lose you anything. So you see you're on it's the point where the scales tip from constructive interference to destructive interference. Up to 120 degrees, you have as little as 0 decibels at 120 degrees to as much as 6 decibels at 0 degrees and anything in between. But up to 120 degrees, there is constructive interference, there is summation. And you can already tell what is going to happen if we venture beyond 120 degrees, because now we start to witness the onset of destructive interference, where we get less out of it than we put into it. Destructive interference. And if we hit our next milestone, which is 150 degrees, you should be able to appreciate that the sum is now 2 times less tall than either A or B alone. If we draw a line over the peaks of the sum, we see that we have 50% less amplitude than the amplitude of either A or B alone. So we're looking at a ratio of 1 to 2. Okay, or 2 to 1, where the sum is 2 times less tall than either A or B alone. And if you lose 50%, then that is functionally a 6 dB reduction. So now we see 6 decibels of destructing interference. You can also see it on the phaser scope. On the phaser scope, this is the 150 degree angle. There we have the 150 degree angle, and notice that the resultant is 2 times shorter than either A or B alone. So now we are starting to lose summation destructive interference. Okay, so let's continue. Let's go to 160 degrees. Let's go to 170 degrees, and then we're about to arrive at our next milestone, which is 180 degrees. And surely what is happening over here should no longer come as a surprise. At 180 degrees, we have sine waves that are mirror images of each other. When we have +1 in sine wave A, it meets -1 in sine wave B. When we have +1 in sine wave B, it meets -1 in sine wave B. And wherever we look, we see them cancel each other out, and that means that no matter where we look, we see perfect cancellation. Same is true on the phaser scope. This is now the 180 degree phase angle between A and B, and I call it the tug of war. I imagine two people pulling on both sides of a piece of rope. These people are clones from each other. They're equally strong, equally potent. One guy wants to go to the right, the other guy wants to go to the left. Nobody's going anywhere, and they cancel each other out. What does cancellation 0, because everywhere we look we have a value of 0. What does 0 become in decibels? Well, 0 in decibels technically goes to -infinity. I cannot show you -infinity within the limitations of Excel, but suffices to say that the -318.2 decibels is pretty silent. But theoretically, this should be -infinity. And here's how you can memorize. Imagine that you have a self-powered loudspeaker and you take out the XLR connector. If you take out the XLR connector out of the back of the self-powered loudspeaker, you're inserting no volts, you're inserting 0 volts into the loudspeaker. And out of the other end comes an infinite amount of silence. And that is how I memorize that 0 is -infinity, an infinite amount of silence. Cancellation. Okay, so let's go beyond 180 degrees. Let's go to 190. Let's go to 200. And then stop at the next milestone, which will be 210. Now, there's nothing special about 210. Everything that we see in front of us is straightforward if you are mindful of the following property. Notice that if we take 360 degrees for a full revolution and we subtract the current 210 degrees, that we're left over with 150 degrees. And that tells us that 210 and 150 degrees are so-called conjugate angles. Conjugate angles. They complement each other, and that means that together they will always form 360 degrees. Over here you see the same 210 degree angle. And what happens with conjugate angles is that the amount of summation that you have is identical. At 210 degrees, we get the same amount of summation as at 150 degrees. And at 150 degrees, the summation was destructive. We started to see losses. We ended up at -6. Well, the same is true for 210 degrees. And just to show that, let me go back to 150 degrees. And at 150 degrees, we will see the same values as at 210 degrees. So once you know half of this story, you essentially get the other half of the story for free. Okay, so let's continue to 20. And then to 230, and then ultimately we're going to stop at 240. Again, 240 brings us to that special place where the peaks of all sine waves are the same, which reminds me of another instance where we saw this. So let's figure this out. 360 degrees minus the current 240 degrees leaves me with 120 degrees, informing me that 240 and 120 degrees are again conjugate angles. And that means that if I know what happens at the 120, I can tell you what happens at 240, where this is now the 240 degree angle that I'm talking about. We can also see it. We can also see it in the phase shift, because everywhere we look, we see that there is 120. What I am saying, this is 120, two minor divisions. This is another 120. So that is 240 degrees of shift. No matter where I look, we see 240 degrees of shift. And again, we don't gain anything. We don't lose anything. Okay. The value, the ratio, the peak-to-peak ratio remains 1:1. So it's again at that point where the scales tip from destructive interference to constructive interference. And the resultant has the same length as either A or B alone. However, if we venture beyond 240 and we go to 250 and then 260 and then 270, at 270 we should be able to predict what goes on, because this situation looks remarkably similar to a situation that we saw before. Let's reason this. There are 360 degrees in a whole revolution, 360 degrees in a whole revolution. Let's subtract 270 degrees, and if I'm not mistaken, this should leave us with 90 degrees once more. And I know what happens at 90 degrees, because 90 degrees was 3 o'clock. And at 3 o'clock, you are going to get 3 decibels. And these are, again, conjugate angles. That is the key word, conjugate angles. It suffices to only know one, and then you get the other for free. Conjugate angles. So, if you get 3 decibels at 3 o'clock, you are going to get 3 decibels at 9 o'clock, if you will. Let's put that to the test. Let's see whether these values are indeed the same. This is 90 degrees, gives me 3 decibels, sure. This is 270, which is its conjugate angle, and it's also 3 decibels, as we can tell from the panel containing the information about the sum of A and B. So far, so good. 280 would be the next step, and then we go to 290, and then we go to 300, and now I'm going to stop at 305. Because what is so special about 305? Well, let's see if we can reason that. Let's take 360 degrees, subtract the current 305 degrees, which leaves us with 55 degrees. And I know what happens at 55 degrees, because that is 555, as in 555. 55 degrees gives you 5 decibels. 55 degrees gives you 5 decibels. Easy to memorize. These are conjugate angles once more, and that means that if you know what happens at 55, for which there's an easy rule of thumb, you can tell me what happens at 305. And look over here, lo and behold, at 305 we get the same 5 decibels of summation as 55 degrees. And here you have the 305 degrees of phase angle between A and B. So let's prove that by alternating between 55 and 305. This is 55, this is 305, and the values do not change. That is to say, the amount of interference, constructive interference, 5 decibels, does not change. Okay, let's continue to 310, 320, 330, 340, 350. I'm 10 degrees shy of finishing a complete revolution, and by the time I hit 360, my blue phaser, my signal B, has completed a single round trip. It's once more pointing in the same direction, and for steady state, for solid state signals, if these two guys are pointing in the same direction, then 1 and 1 becomes 2, and we're back at our starting position where we have twice the amount of amplitude as either A or B alone, and twice the amount of amplitude is a 6 dB increase. You are in time 360 degrees or 1 cycle out of phase. In time but out of phase, 6 decibels of summation. As long as you're pointing in the same direction, you are going to get 6 decibels. If I were to make this 720 degrees or 2 cycles, the graphics are not expected to change. Again, 6 decibels. However, you're in phase and 2 cycles out of time. If I make this 1080, the graphics are not expected to change. You're in phase, but 3 cycles out of time. If I make this 1440, which would be 4 cycles, the graphics do not change. You are in phase, but 4 cycles out of time. And that is today's explanation of adding sine waves and looking at the destructive and the constructive interference. All of this can be summarized in a single chart, which is what we call the phase wheel. When you live at the phase wheel, you will get 6. When your phasors are pointing in the same direction, have equal length, are equally loud, you will get 6 decibels. If your sine waves are overlapping without any shift, you will get 6 decibels. However, by the time you have a 55-degree offset, then 555, which is the rule of thumb, 555 tells me that at 55 degrees phase offset, I get 5 decibels of summation. By the time I am at 3 o'clock, which I can easily memorize, by the time I'm at 3 o'clock, which is 90 degrees, I'm going to get 3 decibels, which is 3 decibels of summation. It's 3 decibels less than the 6 I would have had with 0 degrees, but it's still 3 decibels of summation. At 120 degrees, the scales start to tip. Where we had constructive interference before, we are now going into the domain where we start to see destructive interference. Because at 150 degrees, we lose 6 decibels, and that is called destructive interference. Now we get less out of it than we put into it. At the bottom of the phase wheel, we are at 180 degree offset, half a cycle, and now in theory we should go off the scale, we should go all the way to minus infinity to perfect silence. However, if we continue our journey, then 210 becomes the conjugate angle of 150 degrees. After all, 210 and 150 together sum up to 360, so we see the same amount of destructive interference, a 6 dB loss. By the time we hit 240, which is the conjugate angle of 120, we're back at 0. So now the scales start to tip once more from destructive interference in the bottom of the phase wheel to constructive interference at the top of the phase wheel. At 9 o'clock, we have the conjugate angle of 90 degrees. After all, 270 and 90 together make for 360 degrees. So at 3 o'clock or 90 degrees, you would have gotten 3 decibels. So at 270 degrees, you're also going to get 3 decibels. And 305 is, of course, the conjugate angle of 55. So if you have 5 decibels at 55, which is easy to memorize, then you're also going to get 5 decibels at 305. And then we finish our complete revolution, our first cycle. After 360 degrees, you're back at the top of the phase wheel, and that gets you 6 dB. And now you go on your second round trip, and on your third round trip, and on your fourth round trip. Every time you find yourself at the top of the phase wheel, you gain 6 decibels, whereas every time you're at the bottom of the phase wheel, you lose everything. And that concludes the explanation on the addition of sine waves using the phase calculator. And may it serve you well, and hopefully I will see you during the next video. Stay safe and healthy. Bye-bye.